Next, we'll want to take a look at work when a gas is involved. So imagine that we have a cylinder that's filled with a gas, and we do work on that gas by compressing a piston. So we exert a downward force on the piston moves downward, it compresses the gas, forcing it into a smaller volume. So the amount of work that we're going to be doing on the gas is going to be equal to the force times the displacement of that piston. That's also going to be equal to the pressure times the area times delta Y, because we know that pressure is force over area, and we can rearrange that expression to replace the force with the pressure times the area. Now the area, the cross-sectional area of the piston times delta Y, is equal to the volume change of the gas. And now we can take a look at that negative sign. We know that we're doing positive work on the gas because the force and the displacement are in the same direction, and also we're adding energy to the gas. We're squishing it into a smaller volume, and so the gas molecules are going to bump into each other more and have more energy. So the volume is shrinking. The delta V is negative if we compress the piston. Delta V is negative, and we know we want positive work, and so that is going to be equal to minus P times delta V. So we need that minus sign to ensure that if we compress the gas, the work done on the gas is positive. Now we can look at things a different way. Instead of looking at the work done on the gas, we can look at the work being done by the gas. And the work done by the gas is always the negative of the work done on the gas. Now imagine if, on the other hand, instead of squishing the piston down, imagine we had squished the piston down and we released it. Then the gas would push the piston back up. In that case, the volume change would be positive, and the work being done by the gas would also be positive. The work done on the gas by the environment, in that case, would be negative. So the work done by the gas is always the opposite of the work done on the gas. When the gas is compressed, when the volume, the change is negative, then the work done on the gas is positive, the work done by the gas is negative, and the opposite is true when the gas expands. So in our textbook, W is, without a subscript, is defined as the work done by the gas. You will encounter other textbooks that use the opposite convention. They use plain W to represent the work done on the gas, and it can get kind of confusing. So the important thing to do is to maintain consistency. So we remember that for our text, and when we write down the equation by plain W without a subscript, we're going to mean the work done by a gas, and the work done by a gas is equal to positive pressure times change in volume, so that if the volume expands, that means that the gas is doing work on its environment, positive work on its environment. Now we'll notice that this expression is only valid for when the pressure is constant. So constant pressure process is known as isobaric. So you can think of that as a barometer. Barometer is the root of this word. A barometer measures pressure. Isobaric means same pressure. When the gas is compressed, the work done by the gas is negative. When the gas expands, the work done by the gas is positive. So these are a rewrite of the expressions on the previous page. Next, we want to talk about, well, what happens, because we know these expressions are only true for constant pressure, what happens when the pressure is not constant? In that case, you can make a graph of pressure versus volume, and the area under the curve represented by that graph will be equal to the work. So the work is equal to the area under the pressure versus volume curve. That will tell you the amount of work done by the gas. If you want to know the sign of the work, you have to look and see, is the volume getting bigger or is the volume getting smaller? Are we going from here to here? Are we going from here to here? If the volume is getting bigger, the gas is expanding and doing positive work on its environment. If the volume is getting smaller, if we're following a process like this, then the volume is shrinking and the environment is doing work on the gas, so the gas is doing negative work on its environment. If the work done by the gas is negative, that means energy is being added to the gas by the environment. If the work being done by the gas is positive, that means energy is being taken from the gas is going into the environment. So now we're ready to state the first law of thermodynamics, which I sometimes call the no free lunch rule. So the first law of thermodynamics is basically just a statement of conservation of energy. So the first law says that if a system changes from some initial state to a final state, Q is the energy transferred by heat, W is the work done by the system, then the change in the internal energy, delta U, is going to be equal to Q minus W. So this is just basically saying that if you have a system, its change in internal energy is going to be equal to the amount of heat that you add to the system. So if Q is positive, you are adding heat and adding energy to the system. If Q is negative, heat is leaving the system, therefore energy is leaving the system. And W is the work being done by the system. So if positive work is being done by the system, then energy is leaving the system and going into the environment. If, on the other hand, the work done by the system is negative, then energy is entering the system. So basically what this is saying is there are two ways in which a system can interact with its surroundings. It can either give off or accept heat, or it can do work or have work done upon it. And if you add those effects together, you get the change in internal energy. If we have an isolated system, then that change in internal energy is equal to 0. If a system can't give off or accept heat, if it's insulated, and if it can't do work or have work done upon it, then there's no way for energy to enter or leave, and so the internal energy will remain constant. Now, there are some other expressions we can write down for the change in internal energy. So before we looked at how, if we have a monatomic, so a gas made up of single atoms, so this would be something like helium or xenon, for example. If we have a monatomic ideal gas, then the internal energy is equal to 3/2 times nRT, where n is the number of moles and R is the ideal gas law constant, and T is the temperature in kelvins. So if we have a change in internal energy, if we look at the things over on the right-hand side of this expression, if we have just a set amount of gas, we're not adding or subtracting gas, then n doesn't change, R is a constant. The only thing that does change on this side is possibly the temperature. So what this is saying is that if there is a change in internal energy, there is also a change in temperature. A change in internal energy means a change in temperature. And we know by how much the temperature will change if the internal energy changes, and vice versa. Sometimes this expression is written a little more simply as the change in internal energy is the number of moles times CV. And CV is the molar specific heat at constant volume, which is equal to 3/2 R. Now, this same expression can be used for non-monatomic gases. The same expression is true, it's just that CV will change because it depends on the number of ways the gas can store energy. If you have a monatomic ideal gas, there are 3 ways the gas can store energy, and that's why we have a 3 here in the numerator for CV. So basically you can have kinetic energy by the gas molecules moving in the X, Y, or Z directions. So since there's 3 directions they can move and they can have kinetic energy by moving in any of those 3 directions, there are 3 ways in which the gas can store energy. If you have a diatomic gas, and this is at room temperature, most diatomic gases at room temperature are 5/2 times r. They have 5 ways they can store energy because they can have kinetic energy by moving in the x, y, and z direction. And then because they have a significant moment of inertia, they can also rotate in 2 different directions and store a significant amount of rotational kinetic energy in both of those directions. And so they have 5/2 r at room temperature. Now, diatomic molecules can also vibrate, and their chemical bond can move in and out, and they can have spring potential energy and store energy that way. However, at room temperature, usually there's not enough energy for the collisions between molecules to make the bonds vibrate significantly. So they don't really contribute at room temperature, but at much higher temperatures that are hard to reach, the diatomic molecules' molar specific heat at constant volume can go higher than 5/2. But if you just have a problem where the temperatures are room temperature or maybe slightly above that, then you should use 5/2 times r.